Yeah, I also haven't played, but I'm sorry for bringing in his PlayStation.
Oh, yeah.
Very violent. Very wonderful.
All right, let me get started. We were very excited to have Professor Xingang Chen from Harvard here for the Friday seminar. He got his PhD from the Columbia University in 2003 under the supervision of Eric Weinberg. And he held after that postdoc positions at the University of Florida, Cornell, MIT. And then he moved to Cambridge for Stephen Hawking Advanced Fellow. And he after that he moved to University of Texas at Dallas as an assistant professor, but he finally settled down in the University of Harvard University. So today we're going to talk about the probing the origin of Big Bang cosmology, cosmological physics, and the primal standard.
Thank you very much for the invitation and for the opportunity to speak here. Today I will introduce two research programs that I have been working on in the last few years. Both are related to the primordial universe, the epoch of universe that preceded and initiated the Big Bang, seeding for cosmic structure. I will give a broad overview of these two programs and some interesting connections between them. Please feel free to interrupt me if you have any questions. So we now have a very nice standard model of cosmology, namely the Big Bang model that described about 14 billion years of entire evolutionary history of our universe. The big picture is there. There are some interesting details that we need to find out. But also, when we trace back in time and we recover the initial condition of this Big Bang cosmology, we learn there are some interesting properties about this initial conditions that cannot be explained by the standard model of cosmology, Big Bang model itself. So that makes it necessary to complete this picture at the tip of this evolution and replace the Big Bang model with something else. So that epoch we call the primordial universe. But the leading candidate for the epoch of that universe is the inflation scenario, in which we postulate that our universe at that epoch was sitting on some force vacuum with a very large vacuum energy slowly rolling, driving the universe to expand exponentially. And at the same time, whatever field that present in that epoch will quantum fluctuate. The fluctuation mode gets stretched outside the horizon, mode by mode, in a scale invariant way, seeding. Those become the seeds of the density fluctuations and structure formations later. When the inflation ends and reheating starts, Big Bang starts, all the modes will come back to the horizon. So that's a broad picture. So despite the success of this proposal, there are a lot of open questions. So first is the predictions, for example, that we previously briefly mentioned, the density perturbation being scale invariant to superhorizon. Are these predictions uniquely from the inflation paradigm itself? Are there any alternative explanations? Could there be alternative explanations? If they are, how can we distinguish them, at least phenomenologically? Second is, even within this inflation scenario, we only have very broad brush picture. So we don't know a lot of model details. So we would like to find out through observations in astrophysics. The third question is, this epoch, inflation epoch, supposed to happen in a very high energy scale. Could it be much higher than the energy scale that we can ever probe by building colliders? So this potentially is an interesting playground for high energy physics. So can we learn energy physics from inflation? Okay, so let me give a very broad overview of what the tools that we use, either both theoretically and also experimentally to learn about this epoch. So one of the important tools, probably the most important tools that we can learn about this epoch, because this epoch is primordial and it's blocked by a thermalized Big Bang scenario, and the light we can observe it will be start from CMB, the CMB formations. So all the informations presumably gets homogenized. So how can we learn the information from them? So one of the most important tools that we learn from them is rely on the fluctuations that I mentioned, that is seen at superquantum scales, that is not affected by the process I mentioned. So those fluctuations we call primordial fluctuations. They start with quantum fluctuations, and they evolve. They evolve on the extra horizon during the inflation epoch. And when the universe gets populated through the reheatings, those primordial fluctuations get imprinted in the perturbations of the whatever contents that is created by the reheating. And during the Big Bang model, the horizon starts to expand, and those modes will enter the horizon, eventually seed the structures in the CMB or large scale structure. And we observe them. That's how we that's the information that we rely on. So in terms of theoretical calculations, in order to calculate the correlation functions of those maps generated by these fluctuations, we need to compute a expectation value of a product of these fluctuations, whatever fluctuations that we denote as Q, some operators. We need to compute the expectation value of this operator, and the Hamiltonian here tell us how these fluctuations evolve from very early on to at the end of the inflation. So by calculating this observable and measure this observable in terms of density fluctuations, correlation function in density fluctuations, we will relate the properties of fundamental fields that enter in this Hamiltonian with the primordial perturbations that we could observe in astrophysics. Okay, so the information that we rely on, the observables about the primordial fluctuations, is basically anything traces the largest scales of the contents of our universe. So they could be, for example, cosmic micro background. We know it's a leading order homogeneous isotropic, but there are small fluctuations. That's the fluctuations I'm talking about. And you can also count the galaxy, number of galaxies, and you will be able to see the fluctuations that's seeded by this primordial perturbation. And there's also hydrogen atoms floating around in the universe, not confined by galaxies. So they emit 21 centimeter lines, radio waves. So we, in kind of like futuristically, people also propose to observe the distributions of those 21 centimeter emissions. So that could be another tracer of the density fluctuations. So anything trace the largest scale contents of the universe. And once we map out those maps and study the correlation functions of those fluctuations, we can compute 2-point correlation functions, 3-point correlation functions, and those are generally called 2-point called power spectrum, 3-point function sometimes called bispectrum, and 4-point trispectrum. They are non-Gaussian entities. And they are broadly speaking, two properties of those correlation functions. One is scale dependence. So given any correlation functions, you can rescale all their case by a common factor. So that's called scale dependence. And except for the 2-point correlation function, any other correlation functions, you can also roughly fix the order of magnitude of all case, but you can change the shape of the triangle or 4-point correlation functions. So those dependencies called shape dependence. Yeah. Okay. So now with all these tools, so let's start to introduce the first program, which we call Cosmological collider physics. The motivation of this is the following. So let's start with the inflation paradigm. So in inflation, we know that we need a field which is called inflaton that sit at the top of the potential for quite a long time, 6 epochs. So they can sustain, they can drive this sustained period of inflation period. For that to be happening, you need the mass, which is basically coach at the top of potential, to be very small. How small? You need to n. There's h squared capitalized energy scale of inflation. You need them to be roughly 1% or less. But on the other hand, we know if you have a lot of light scalars, they can be coupled with the curvature background, or they can have radiated corrections. All those corrections will naturally introduce a mass scale which is h squared for them. So you need to rely on either some kind of symmetry or cancellations to tune this generic mass scale into at least one of them to 1% of them. So that's called eta problem. So that's a problem of model building, and we assume it's achieved at least for one field. But once this is achieved, you also know that if you look at the spectrum of inflation, it will not be just one inflaton, right? So we already give argument that there's a lot of them should be of order h, and certainly there are many other fields which stabilize low energy theory. They are necessary to exist with mass larger than h. So there's a full spectrum of particle physics during inflation. The question is, what are the observables of these particles besides this very light inflaton? Okay. So because the energy scale of the inflation is of h, all those particles which has a mass around h, we already argued there should be quite a lot of them. They are, although not classically excited, but quantum mechanically will be excited because the inflaton, the inflation background can be thought of as a thermal bath with a given Hawking temperature of order h. Higher mass particles will also be excited, but there is a penalty caused by they having mass much larger than this typical temperature. So it's similar to Boltzmann suppression. So those particles will be quantum mechanically created during the inflation background, and they also will decay into the inflaton fields through couplings, and eventually at the end of the inflation, those information will be recorded as intermediate particles that affects the properties, scaling property, shape dependence property of the final converging functions that we observe of the inflaton or some curvature field. Yeah.
Yes, so for the mass, are you distinguishing between just a mass obtained via coupling to the inflaton, which gets a mass of order h, or just an intrinsic mass like a gut scale?
Yeah. Yeah, that's very interesting because both of them exist. For this program, I do not tell the difference between them. So all I need to know is whatever particle intermediate, what is important to me is its mass, or in the future you will also see its spins or its parity.
So you don't care how the mass is generated.
Yeah. So this is not going to probe how this is generated. It's going to tell us once generated with the spectrum. So that's a very interesting question because we also want to know where it comes from. So basically, given a particle physics model, you need to run this particle physics to the scale of inflation. And you will see the particle spectrum, for example, standard model will be completely different now and in the background of inflation. So you need to know the whole story in between if you want to do this in a UV completely way. Yeah.
But you care about, well, if you have gut scale masses, then those are gut origin masses, they're just gonna always be gut scale masses.
Yeah, so if they are lower than H, so it's unlikely they will be affected by H. Yeah.
Well, but if you take the standard model, they might be affected during inflation, but then during reheating, they'll presumably have their weak scale masses.
Yeah, they will have mass again. So the program, the thing I'm probing here is their mass during inflation.
At the very end of inflation, or?
End of inflation and the beginning of inflation is roughly the same because the scale invariance says that the energy scale is always around H.
Yeah, but
Later, they will come back, not come back, they will become the standard model particles. But the signal I'm talking about, at least the simplest version of them, will not be able to probe the mass they recover after reheating. So we will only probe them, probe their identity during inflation. Yeah.
But that requires very specific, I mean, if it's the standard model, you have to couple to the inflaton
Yeah,
in a very special way.
yeah,
As opposed to having particles already there where you don't have to do anything.
yeah, that's exactly right. Yeah, you have to, for example, if you want to probe standard model particles, you have to assume some kind of couplings because inflaton is a scalar field. You do some effective field theory, just couple them, and you give a cutoff scale. And there will be a very important question to say how strong is the signal. So it's actually a very important question. If it's too weak, but we know that at least couple gravitationally, so there's a signal there, but we are not going to measure them anyway. So it's an important thing to say, for example, in effective field theory, how large is the signal? Is this observable in principle? Or it give you the most optimistic case, how large is the signal? Yeah, that kind of question. Yeah. Okay, any other questions? So if not, let's see some details how those properties of those fields will manifest in the collision function of inflaton. So let's first look at the behavior of those particles, massive particles, not inflaton. And for those massive fields, their wavelength start out to be much smaller than horizon size, and then they stretch become larger than the horizon size. So during the process, they behave very differently. So when they are well inside the horizon, they are just they don't feel the expanding background. So it's like a boundary with like a flat space quantum fluctuations. But when they are getting stretched near and outside the horizon, they will behave as a power law in terms of this conformal time. So they basically decay if this mass is between 0 and 3/2. So basically, for example, inflaton mass equal to 0. So this quantity will be 3/2, it cancels the 3/2 here. So that means the for massive field, they will remain frozen outside the horizon. But for massive field, they get diluted. So there is a decay behavior. So so we have a power law dependence here. If the particle is very massive, it's a little more massive than 3/2 H. The deep inside the horizon, their behavior is still similar, still same, but outside the horizon, they also oscillate. While also gets diluted, the amplitude decay, but the oscillations here. So those two different behaviors, when they come to inflaton, will lead to characteristic different behaviors of the imprints in the collision functions, although they can be analytically continue to each other. So for the lighter massive fields, the long wavelength massive fields will modulate the infraton mode because you have this modulation. But for the more massive field, the oscillation not just modulate the infraton, they will resonate with infraton because infraton at that time is still within the horizon because we consider long wavelength mode of massive field. So those two oscillations at some point can resonate because everything's time dependent and imprint their signatures in the infraton in that way.
But now you're assuming some specific coupling?
There will be couplings, yeah. So we are assuming, definitely we need to assume coupling because so this is not like particle physics, we can observe many species of particles. We can only observe the cohesion functions of infraton, or in some extended paradigm, we can also observe maybe curvaton. But not many possibilities. So every fingerprints of the massive particles has to be imprinted by assuming they couple to infraton in some way, like in terms of effective filtering operators. Yeah, that's definitely necessary. Yeah. But with this couplings, these two behavior modulation and the resonance happen.
Sorry, but just one question. So to have a large resonance,
Yeah.
coming from the overlap between the mode function of the this massive field and the inflaton.
Yeah.
I think the frequency here is determined by the mass of heavy field.
Right.
So to maximize the resonance, I think the massive field mass should be comparable to the inflaton mass.
Yeah. So I will
Is it true?
talk about this in more details, but roughly you can think of that way. The resonance always happens because the massive field will set the frequency, so it's a fixed frequency that's determined by the mass. But the infraton field start out. You can have very short wavelength infraton modes. You consider that's a very short wavelength, large K infraton modes. So those wavelengths start out very high, much higher than M. And then the inflation stretch them, so the frequency decreases all the way to almost zero until they're frozen. So they scan. So the mode by mode, there's always one resonance happening.
I see. Okay, I see.
Okay, so what if the particle has a spin? So if you have a spin, so again, you can look at this long wavelength modes of the massive field, and the blue is a short wavelength mode of the infraton field, and the coupling is introduced here, and you need some couplings. But the point now is, if you have a spin in these intermediate particles, there's a projection, just like particle physics, between these two momentum modes, and that will project about a factor which is given by Legendre polynomial as a function of this angle, which is the angle that you can measure in the collision function. And the subscript S is the spin of this intermediate state. If you okay, so if you work out details and you can summarize the whole story in the following way. So there is a soft limit. Soft limit means one of the modes has to be small. One of K has to be small, which means that the K typically is the K mediated by the massive field. So in the soft limit, there is a relationship between the non-Gaussianities, the soft limit non-Gaussianities, and the particle spectrum of whatever energy physics present during the inflation. So, for example, if you look at squeeze the limit of a 3-point correction function, which is called bispectral, you have two distinct modes. One is long modes and the short modes. And this 3-point correction function will behave as a power law of this ratio between the two momentum with some angular dependence here. So if you measure, if we can measure this bispectrum, then the power in this momentum ratio will tell us the mass spectrum of this theory, and the angle here will tell us the spin of this particle. And this factor tells us if you're trying to observe a particle with mass much larger than h, and the signal will be suppressed by a Boltzmann suppression. Okay, so there are several important works that eventually lead this result. Initially, we studied the scalar field with mass less than 3 of h because it's not Boltzmann suppressed. In this case, as you can see, the power law here, this mu is imaginary, so this power is actually real. Then later on, it was extended to larger than 3 of h case by Nomi, Yamaguchi, and Yokoyama. They didn't derive the Boltzmann factor. And then Akane, Hamid, and Morosenda has wrote a paper among many other developments extend this formula to both the heavy mass case with Boltzmann's factor derived, and also generalize them into the higher spin case. So the name, there's also the evolution of the name of this program. So initially we call this single field inflation because it's classically it's a single field, but quantum mechanically it's many field inflation. But after 2015, Akane, Hamid, and Morosenda came up with a nicer name. People liked it a lot, and everybody can understand what that means. It's called Cosmological collider fittings. So we take that name now. Yeah.
So just make sure, just to make sure my understanding is correct. So when mass is smaller than Hubble, like the Boltzmann suppression factor becomes complexified, so then you can avoid Boltzmann suppression, right?
Yeah.
Okay.
That's
and then that's the case. What you're
we
probably
usually study that
very
because so theoretically it's also interesting to study the whole case. Basically.
sure, yeah.
So it's not limited by observational constraint.
Yeah.
And saying, well, in principle, you can measure the particle contents of the universe. All particle contents. The imprint, no matter it's direct coupling or Gaussian coupling, imprinted, they're all imprinted there. It's just experimental. The experiment's not going to tell all of them. Yeah.
Why did the Japanese group? Why did they miss this Boltzmann suppression factor? Is it because they want to emphasize oscillatory phase or oscillatory signature?
They should be there, but they didn't do it. Yeah.
Okay.
Well, of course, it's better if they divide it. Yeah.
But they mentioned it, right? They mentioned this. They should have mentioned this
Well,
suppression
we
factor.
mentioned that already, but we don't care. We say we mentioned they should be a Boltzmann suppression, but because it's suppressed, so let's study the unsuppressed case first. Yeah.
Okay.
But I think Morosenda and Akane, Hamid, they derive them vigorous. So that's the point.
So
But they also introduced a lot of computation tools that also they study more general case.
Yes.
Yeah. So I will mention that later. Yeah. There's a lot of things.
So as far as I remember their paper, they were talking about deep into the future when we discover like a lot of new modes through 21 centimeter kind of cosmology, which is yet to happen, right?
Yeah.
I have a question, like what can you deduce about this sectors idea or around the Hubble scale now from the current data?
What can we do now? Yeah.
No, but like if it's one particle with a mass slightly larger than Hubble, probably it's not that directly observable currently, right?
Yeah.
Well, what is like I need to do? Is it 100 particles? Is it 1,000? How many should I add to have observable effect now? Right?
Yeah.
So what are the current data?
Yeah. So that's a very important question. I'm going to come back to give you some outlines what's happening. But the quick answer is it's very model dependent. Even one particle can be observed. 100 particles also be observed. But the most important point is the coupling between infraton and them. So if they couple with a larger coefficient, so the signal amplitude will be larger. So that's the bottleneck.
Okay.
So if it's only minimally gravitational coupled, the signal is too weak too.
And if I have a prior that the coupling between these new fields and the inflaton doesn't spoil the flatness of the potential, does anything remain?
Yeah, of course. We always if you propose the scenarios, inflation, you have to make sure inflation happens. So, so the coupling, for example, we introduce will, for example, the simplest way to introduce the coupling is to introduce a coupling that respect the shift symmetry of the infraton. Yeah. But still a lot of model dependent details. So this is also why in the second program, I'm going to talk about Hall effect. So there is aspects of that, which is much easier to observe in Hall effect. I'll come to that. Yeah. Non-causality obviously is much more difficult, even both in computation and also in terms of experimental sensitivity. Since then, there's a lot of developments in this field, both in computational formulas and model building and observational aspects. So to give a broad overview, I'm trying to list some of the most important questions that people has investigated. It's not going to be, I'm sure it's not a complete list. So if you have more questions, please feel free to let me know either during the talk or after that. So this question has already been asked even here for many times. So the most important question is how large can you make or for those signals which are called collider signals. I think I skipped one quick slide. Yeah. So basically I'm saying this signal which bear the information of the new particles is called collider signals. And as I mentioned, there are two kinds. One is momentum ratio with a real power law. We sometimes call it power law collider signal. Another is imaginary power. Imaginary power that makes the dependence oscillatory. So it's sometimes called oscillatory collider signals. I will explain later. For some important reasons, we also call this clock signal. So the amplitudes of the collider signal are very model dependent. You got your question that you asked. So it's open for model building. So there are several situations that people have investigated how large this coupling can be. Now, the first one is if the massive field has self-interactions, those massive field is not restricted because it's orthogonal to the infraton trajectory. So they are not restricted by the Sorel conditions, which is the condition that makes the non-causality of a normal inflation model so difficult to detect because the flatness just kills the interactions. So if you have unrestricted self-interactions, that can boost the signal a lot. And also you can make use of the fact that the infraton is rolling actually quite fast in terms of h square unit. So you can use this through a chemical potential coupling to the new particles. If you Lagrangian introduce that kind of couplings, they will boost the signals in the sense that the energy scale of a cosmological collider can be boosted by order of magnitude above h. And also, this is another possibility that I will concentrate and discuss in much more detail later. You can introduce some primordial features that breaks the scale invariance of the inflation field, which effectively amounts to injecting extra energies to the inflation background. And also, you can start to ask questions how this high energy probe can be used to probe a variety of particle physics models. And there are a variety of possibilities that people already investigated. Some of them are just starting. For example, supersymmetries, or just asking what's the standard model of predictions for and all its minimum extensions for this cosmological signal. And there are a variety of gauge bosons and neutrinos. What are their signals in cosmological physics? You can investigate as high as possible the energy scale of the inflation as well as particle physics. And they are related by the Guppy inflation, electron genesis, isocurvature mode, gravitational waves, and also very interesting topics. And also, we mentioned the mass spectrum and the spin spectrum can be probed by the collider signals, but they're also parities. So people have figured out how to compare the configuration. Now you need a 4-point correlation function. to figure out the parity of intermediate particles. And there's a decay wave as well. And also you can extend this in terms of effective field theory to a variety of different operators. You can ask, what if it's a non-productive couplings? This is a question of a strong coupling limit. And also you can ask how to extend this to a higher mass limit. Okay. And because of the mode function of a massive field is much more complicated in inflation background than the flat space background. So the computation of the number of entities, even if you propose a reliable model, is actually non-trivial at all. For example, people, because of the computation of these mode functions of massive field, have been using numerical calculations beyond some squeeze limit, because the previous formula that I presented is only applied to the squeeze limit. Right? So the measurement you want to measure the whole configuration. Squeeze limit is easy to compute, but the whole full configuration is difficult. So we oftentimes rely on numerical calculation. But in the last few years, there's a dramatic development in how to compute those signals analytically. There are basically two camps, I think. One is, roughly speaking, just apply the E information, but try to use some clever techniques. You can read them. I'm not going to explain the terminologies, but some clever techniques to expand the massive field mode functions and then sum them later, so that you can analytically, in many cases, in closed form, analytical form, obtain the expression of correlation functions. Another very ingenious approach led by Akani Hamid and Monsena and Bauman's group, they are trying to compute those correlation functions directly from symmetry principle unitarities without going through all the integrations. So that's called bootstrap. So the most important question is observations then. So given the predictions that we talk about, we can ask the questions, is there already constrained? Are they already constrained by observations, right? So people did compare a lot of them to experiment and so far find a variety of constraints. So those data include the CME temperature and polarization data, including the galaxy surveys, and there's also forecasts either galaxy surveys and also the 21 centimeter hydrogen information. Okay, so now let's move on to any questions before we move on to the second program. Okay, yeah.
Can I ask one simple question? So when you want to enhance the correction to the P zeta K or the bispectrum, I think it's unavoidable for you to use some temporary the fast velocity, the large velocity of the inflaton, so that induces also the large velocity of other heavy fields. I think that's unavoidable for you.
Yeah.
To enhance the
inflaton velocity, I do not need to make them large. They're already very large. Despite the name of slow inflation,
yeah.
If you work out 5 dots,
but that's not enough for you, right?
3000 h squared. So even you would take a square root, it's about 60 h. So it's actually a pretty high velocity. So that velocity, when you derivatively couple to a whatever new massive field you want to probe, you can actually create some large signals, even if the mass of that particle is somewhat larger than h.
Okay, I ask this because, like, if you require really high temporary velocity of inflaton, that give rise to the suppression of P zeta K actually, because the P zeta K is inversely proportional to pi squared.
I agree with your statement.
Yeah.
I agree with your statement.
So you need to pay the price, right?
Yeah, but I do not need to require them to be large to start with. They are already very large. If I want to make it larger than 60 h,
I see.
then I will suppress.
But you don't require that.
I don't require that.
Okay,
So actually, I fit the data of P zeta K, 10 to minus 5, 10 to minus 10, 10 to minus 5 squared, and I get 3600 h squared. So that's actually a very firm observational implications. Okay, so the next program, the question I'm asking is, can we observationally distinguish the inflation scenario and some possible alternative to inflation scenarios? I'm not going to build in alternative inflation scenario here. I assume if there is such scenarios, can we distinguish them in a model independent way? So model independent is very important because you can always distinguish one model with another model. Okay, so first some very broad, brief overview of the situation in this primordial universe building field. So inflation, as I mentioned, is the most studied, least problematic scenario to explain all the problems that we have. On the other hand, there is several classes of alternative inflation proposed. They are much less well developed than the inflation model itself, and they typically have more problems because each of them has a problems, but they have more problems than inflation. But at least if you look at some of the point model of alternative inflations, for me, it serves as a reminder. It serves as a reminder, a kind of eye opener, that several key predictions of inflation may not be unique to the inflation scenarios. There could be other possible explanations. So those scenarios should be explored and at least experimentally tested. So I just give you an example. What do I mean? So for example, we know the perturbation is seated at superhorizon size. That's verified by experiment because we have acoustic oscillations. They enter horizon at the same time, generate acoustic oscillation peak in CMB. So naively, you will thought it's obvious property of the inflation scenario only because all the fluctuations start from subhorizon, they got to be stretched outside the horizon, right? But no, but if you look at another scenario, contracting scenario, the interesting thing is the horizon scale of the contracting scenario does not remain constant. They actually shrink. They shrink in a way that's even faster than the scale factor shrink. So that means eventually you wait for a while in the contracting scenarios, you end up with a scale with a super horizon fluctuation too. So you just they are equivalent up to a rescaling. So okay. So the third motivation to study the observational prospect of the distinction between inflation and alternative inflation is even if I really like inflation, I don't think all the other are going to work. So I'm only going to study inflation. Inflation still have many observables. So it's interesting to know among all those observables, which are the observables that can be used to distinguish one model, one inflation model from another inflation model, and which are the observables that actually relate to defining property of the inflation itself, common to all models. So in fact, I will tell you an example slightly later that if we do not think about alternative inflation at all, we actually will miss some important information, even if we are presented by the predictions. So that means thinking about alternative inflation does help a lot, even for this purpose. Okay, so why we think about alternative inflation model? Let me make also another analogy. So about 100 years ago, we observed the stars, and the image of the stars is actually two-dimensional. It's very difficult to figure out the distance of the star between the star and us. So that's one of the key problems of astronomy 100 years ago. So this led to debates on issues such as is sun the center of the galaxy? Are there any stars beyond the Milky Way, for example? And all this problem is solved when people discovered standard candles, such as Sapphire Type 1a. So basically turn a stack of 2D images into 3D. Actually, the current situation for primordial universe cosmology is similar, but in a different way. So we observe the information of that primordial cosmology by observe the density perturbation, for example, the power spectrum, right? The x-axis of those plots are modes, and the y-axis are amplitude. So those information are 3D informations. But those informations are generated when the different modes are exiting the horizon. Once they exit the horizon, they get frozen. So they exit the horizon one by one. So they are generated at a different time when they exit the horizons during primordial universe. So each mode you can think of is a snapshot of primordial universe. And we just stack all the snapshots here. Okay. But now the question is we don't have time coordinates. So it's exactly almost like we have a row of film frames, we have a stack of snapshots, but we don't know how to play the film. So there's no time coordinates. So this is actually the fundamental reason there is still confusion between inflation and alternative inflation. If you look at the two scenarios, they're completely different. One is exponential growth, another is a slow contracting. But they still leads to very similar properties because we don't know how to play the film. So the key is, so this led to a lot of debates about primordial universe being either inflating or contracting, or if it's contracting, whether it's slow contracting or fast contracting. So we need to find, analogous to standard candle, some kind of like standard clocks that can put steps on the frames of this row of frames to turn them into a film. So so the question we ask is there any observable that you can use to directly measure A as a function of T? So the T time coordinate is there. So the answer is actually in principle, yes, because all the massive fields that I mentioned above previously, if you take a subset of them which has a mass slightly larger than h or much larger than h, which is actually the particle that we initially ignored, you can use them to directly probe A of A. So because now I'm talking about more than inflation scenarios, so I have to define what do I mean by massive. So by massive, I mean the mass is larger than the event horizon scale of the primordial epoch. For the event horizon scale of the inflation scenario is h, but for some other scenarios, they may not be h. They can be very different numbers. The unit is h, but there's a numerical factors that determined by particular scenarios. And it also can be time dependent, unlike inflation, it's time independent. Okay, so just to explain some basic ideas of how this works, we call them primordial standard clock, because for a field with mass larger than h, they don't feel the expanding or contraction of the background. So they sit there and harmonic oscillates. On the other hand, as I mentioned, we observe correlation functions through infotons. Those infotons are approximately massless field, so they also oscillate, but their oscillations frequency changes with time. So they start with boundary with high frequency oscillations, and later when T goes, they become low frequency in terms of the coordinate time T. Here, this is conformal time T, and they're related by a scale factor. So now you have two oscillations. When you compute the correlation functions, so the question one of question previous asked by the audience, but now I'm making it more mathematical. So you have the product of these two products, because these oscillations will typically come in as a coupling of the infoton fluctuations or curvature field fluctuations if it's not inflation. And you have to integrate over time. So if you look at this integral schematically, the integrand oscillates, and so they mostly cancel each other until you have a resonance, which is the stationary phase point. So this is the stationary phase condition. So if you say T star, tau star are the stationary point, you can work out the resonance condition. Basically is A T star equal to Kn. And this is easy to say because this basically tells you M equal to physical K, which is K over a scale factor. Okay, so now you plug back in to this stationary point result. What you have to do is you basically just inverse this function. So whatever function this is, the inverse, take the inverse. So take the inverse function, and now you say the correlation function now has a phase as a function of K. So this no matter tau or a, but no matter the function t and tau, they're all related. But this tells us the scale factor as a function of t, which is this function, is now inversely and directly encoded in the phase of this signal as a function of k. So measuring this phase as a function of k, you actually read a of t. So that's really why we call it dot signals.
But this
Yeah.
resonance should happen after semi-mode exit the horizon. Otherwise, it's meaningless, right? This resonance should
It
happen
happen-
after semi-mode exit the horizon, of course.
Yeah.
Because,
Yeah. So
because
those
we cannot
horizons
observe the larger scale than
those
scales.
those also resonance happening deep inside the horizon because M is very much larger than even the horizon scale.
Yep.
Yeah. So they happen and they imprinted in the amplitude and they exit the horizon, they flows. Okay, I will review it. So there are two ways this clock signal can be imprinted. One is classically, another is quantum mechanically. So what is the classical way of doing that? So in order to imprint this in a classical way, you have to break the scale invariance a little bit. You have to introduce features like sharp features and periodic features. And to motivate that, you can think about this in the context of inflationary landscape of potentials. So even if you think about single field inflation, you actually think about some complicated trajectories in the low energy value of this potential. So sometimes they turn and they will get overshoot to the orthogonal directions, excite some massive field oscillations. So that on average still preserves the scale invariance, but the small deviation that conventionally ignored for this purpose will be very important because they excite the oscillations.
Can you give
of
us
massive field.
can you give us an observational motivation for this sharp feature?
I'll come to that.
Okay.
Okay, so you have a sharp feature and you also have massive field. Okay. Whether either inflation or non-inflation. So those two signals are very different. So in order to study them in a model independent way, I'm not going to build the alternative inflation. I'm just going to parameterize the alternative inflation by saying the scale factor of this primordial universe is a power law. So it actually covers all the proposals that have been made in the literature. For example, P larger than 1 is actually inflation. It can be power law inflation. If P is infinite is an expansion inflation. So this, if P is within 0 and 1, and if it's order 1, it's called a fast interaction. A primary example is matter interaction. If P is close to 0, it's the paralysis scenario. And also same thing. If you make P negative, you have this, you represent a slow expansion scenario. So now here is a result in terms of a rough sketch. So you have two processes, sharp feature and then oscillator massive field. So they actually generate a very characteristically different signals. So for sharp feature signal, although they are model dependent, schematically they are all same in the sense that they are sinusoidal oscillations. But once the massive field gets oscillates, because the resonance that I mentioned previously, there is a direct encoding of the background evolution to the phase as a function of k, and you start to see a scenario dependent. It's also model independent within the scenarios. A scenario dependent signals for different scenario for different cases. For example, for the inflation case, you will see the wavelength of this resonance signal increases as a function of k. And same, if you have expansion scenarios at different speed, the wave function increases. But if you look at the contraction scenarios, the wave function, the wavelength of this oscillation decreases with time. And also a fast scenario, the difference between fast and a slow scenario is, in fast scenario, you will see a lot of resonance, but in slow scenarios, you only see a few ticks. So basically, this is just a pictorial graph illustration of the mathematical formula I mentioned previously. I will skip for time reason a more detailed discussion. Basically, I'm explaining how how those sketch is represented by mathematical formula. And I'll only emphasize the last one. So this is actually the phase dependence on the K modes. K can be power spectrum, K1 plus K2 power spectrum. You can also use K equal to K1 plus K2 plus K3. There will be non-Gauss entities. So all those are constants. So the dependence of K is directly the inverse function of A of t. So this phase pattern is a direct measure of A of t, as I previously heuristically explained. Okay. So now the massive field can also oscillate, of course, without sharp feature. They can also quantum mechanically. So they always exist persistently in any time-dependent background. So the story is actually very similar, but now we call this quantum primordial center clocks for obvious reason. The story is very similar. So the massive field is now no longer classically oscillates, but they also have a quantum oscillations. When the wavelength of this quantum fluctuation gets stretched close to the horizon or even exit the horizon, the behavior of this quantum fluctuations is actually harmonic. So it's very much like classical oscillations, because they are the oscillation scale now is always much heavier than the horizon scale that in the story. So instead of coupling the classical oscillations with the infiniton quantum fluctuation, now you can look at the three-point correlation function, in which the quantum fluctuation of this long wavelength massive field coupled to the short wavelength infiniton field. So as I mentioned, this long wavelength mode oscillates harmonically. So for the short wavelength mode, the effect is almost similar as a background oscillation. Okay. So this is a qualitative reason, a simple way to explain why the end result turns out to be so similar. But except that you replace a scale dependence, which is capital K in the previous case, by a shape dependence, which is ratio between K1 and K3. So everything else in the phase pattern is the same. So now instead of a scale dependent oscillatory signal, you have to work harder and find the non-Gauss entities and look at the shape dependence of all the signals. So they will tell you A as a function of t. Okay, so now come to the connection between these two stories, and also a place that I like emphasize. If you only want to study inflation, but you do not think about atomic inflation, you may miss some important information. So we did this separately as two programs. I didn't expect that they are so closely related, but after all these consequences work out, and we find a very interesting connection between the primordial standard clock and the cosmological phases, because after all, they all study massive field. So if you now, I look back to this formula. So this formula tells us, as I said, all the information on particle spectrum, mass, spin, and mass spectrum, spin, and also Boltzmann suppression factors. Now, initially we thought this exhausted all the possibilities, right? So information that we can extract from the experiments, because what else can we get? Because I just exhausted all the factors. So that's all the information. But after we studied this primordial standard clock scenarios, we realized now, if you look at the case when m is larger than 3.5 h, and this power law dependence actually is very important, because you can write the power law in terms of sign, and you look at the argument of the sign, there's actually a log here. So why this is a log? Because we implicitly assumed the inflation is exponential inflation. So this log is actually an inverse function of exponential. So this is why the log appeared here. So that means actually besides measuring the particle spectrum, there is also a very important piece of information, which I think even more important than particle spectrum, is if you measure this and you fit data and you find the dependence is a log, that actually proves the scale factor of the harmonic universe is especially growing. So which is the definition of the inflation. So this property is actually a property intrinsic to all inflation models, and there's not a model dependent fact. Okay, so let me quickly go through some remarks on the alternative to inflation, and also quickly some observational perspectives. I think I'm not able to finish some of the slides that I will come later, but I will give you the rough summary. So if you have inflation versus non-inflation, so inflation that I mentioned, people call this cosmological collider because you have a fixed energy scale, and you have particle spectrum, and this scale will talk, and particles happens to be around that energy scale, not much higher, can be below. But for the alternative inflation scenarios, the horizon scale changes. The mass scale of the horizon increases. If you have particle spectrum sitting there, and actually it's not a particle collider, it's actually more like a scanner. So it scans the whole spectrum of particle physics and leaving the signal scale by scale. So it's very important, interesting distinguishing between them. And also some near-term observational prospects. And near-term, I mean CMB polarization and power spectrum. Those are the cleanest signal about primordial observations that we will get. Also, galaxy formations, larger scale structure. I'll just briefly mention them. But these are the cleanest ones. So what are the prospects of probing some of the theoretical conditions that I mentioned previously? So I will just concentrate on power spectrum, which is the one related to the breaking of the scale invariance. If you're interested, you can ask me about the non-Gauss entities after talk. So there are some. There's a question from the audience. So what's the motivation from
Sharp feature,
Yeah,
inflation,
feature.
inflated potential, yeah.
So we don't have evidence for that, but there are some interesting suggestions that that may be there. And I just give a landscape argument, but this is an experimental one. So if you look at the CMB, and there's a famous glitch over here, sitting there. Everything's W map. Yeah.
Is it statistically
None of them are statistically.
incompatible with the cosmic variance?
Yeah. So all I'm going to talk about data so far is statistically consistent with the standard model. Yeah. So otherwise there will be big news. Yeah. So I use this as a training to build up a pipeline and waiting for future experiments. Yeah. So but this is some suggestions.
I
So
ask another question. Given that you measure it over lots and lots of nodes, you should expect at some point where there will be like an excess or a glitch one way or another.
yes,
You know.
actually come to part of your answer to part of your questions. It's a very important question. So first of all, you want to make sure that there's no systematic errors, right? But also there are many different possibilities. Even model building can introduce glitches.
In particle physics, it's called look-elsewhere effect. If you
Exactly.
have
Exactly.
if you have
I'm going to answer that question. How do you make statistics rigorous? It's a very important question. Anyway, so you build a model and you compare, and because the model you introduce will have more parameters than standard models. So the question you ask is very important. How do you cannot just compare chi-square because you have more parameters, you will have a better chi-square. So a mathematical rigorous way to compare that, which takes into account looks elsewhere effect, is you integrate all the parameter space and the likelihood, and you compute the z, which is likelihood for different models, and you take a ratio, which is called Bayes factor. The Bayes factor not only takes into account the penalties that you should receive by introducing more parameters, but also taking into account all the parameter space that you scan through, look elsewhere. So after do that, there is like a category which tells you how strong the evidence of your model is, which is called the Bayes factor. For example, if you compute log, if your log is very close to 0, now your model, although you have much better chi-square, it's not worth more than a bare mention. So it can start to get qualitative. And if your model has a Bayes factor, log Bayes factor between 1 and 2, we call this substantial evidence. So on. So we take that exercise, and as expected, this model, although has some, I introduced, basically the model I introduced is some model encounters a glitch and do some sharp feature, generate some sharp feature signal, and then oscillation of massive field. So they do give you large chi-square, better chi-square, but because I have 6 more parameters, this model is not worth more than a bare mention. So, but we build pipelines on that because in the future, there will be several polarization experiments, which is built primarily to detect the B mode, another way to distinguish inflation in alternative inflation. But to measure the B mode, you need to measure E mode pretty well because E mode is a bad one for them. So, but we just take the E modes. Even if you don't have B modes, we take the E modes, which is almost cosmically cosmic variance limited, and we ask how much better constraint can we place on those candidates that we identified, but not significant statistically. So those including Simon Observatory, Lightbird, or futuristically CMB S4. So okay, so I'll just tell you the conclusion because I'm running out of time. So we ask the questions is how the future CMB experiment is going to test those candidates. In our second question is if optimistically one of some feature gets detected, can we use this experiment to distinguish different possibility of feature models? And the conclusion is within the set of the experiment that I mentioned in the previous slides, and within the candidates that we identified in the Planck CMB spectrum, we introduced many different feature models. Those are not related to massive field, and some of them related to massive field. The conclusion is if the universe is truly featureless, no feature models, all these candidates can be rolled out in a generally strong sense, in the Bayes factor, strongly rolled out. But it's never decisive, which is actually bad news for harmonic feature models, because the feature models, you can always tune the amplitude to be 0. So they are always continuously connected to the standard model. So you can not really rule it out, but you can provide strong evidence. But the situation is very different if you detected a feature models. If you detect feature model, you can rule out the featureless lambda CPM model with a very strong evidences. And even better, you can even distinguish different types of feature models with evidence ranging from very strong to decisive. Okay, that's the conclusion. And also, I only talk about CMB, and there are also very important experiments coming in the next decades. And continuously right now about galaxy surveys. And futuristically, there are also possibilities of 21 centimeter, even stochastic gravitational wave, because they trace density correlation as well. And of course, I only look at the 2-point correlation function. You can look at the 3-point correlation function, 4-point correlation function. You can also look at the isocorrelation perturbations. Yeah, that's all for today. Thank you very much. Yeah.
Thank you so much.
Oh.
Do we have more questions?
So in the cosmological collider physics, you already shown there's a lot of work on the model dependence of the spectrum, which again later on you already made a connection to your standard clock physics, right?
Yeah.
Which means the dynamics of the massive field actually will heavily impact your standard clock as well, I assume.
Yeah.
But what you critically rely on your predictions for
Exactly.
the standard clock to extract the information. So
Yeah.
in that regard, you have very strong model dependence in how you use it as a standard clock.
Yes. Yeah, exactly.
How would you address this
Yeah.
problem, right? Whatever we observe, it is going to have
Yeah.
huge. Actually, I don't know even if I have precise predictions there.
So exactly, that's a very good question. So when you search them and constrain them, you experiment, you cannot do model independently. You came up with templates, which characterize one categories of models, and then you compare these templates with experiments, and you say whether these templates can be detected, or if not, how much it can constrain. Yeah. So for the purpose of a standard clock signal, within the templates, there are many different features. Only one feature is useful to measure A of t. All the others tells you model-dependent properties of inflation. So that is why you can separate the properties.
Yeah.
Right? Some of them tell you model-dependent, some will tell you the defining properties.
Maybe I should view it as a inverse problem. Let me observe some features first and
Exactly.
try to map to the.
So when you observe features, there's also several features that I introduced here has nothing to do with massive field. So there's a lot of things to do, but I show some optimistic aspects of. Yes.
So what features of CMB polarization measurement do you need? Is it E modes, measure good signal to noise
Yeah.
over a large fraction of the sky?
Yes.
What do you need?
That's the only thing we observe. So you measure E mode up to near cosmic variance, or maybe close to that, from large part of the sky. And those are interesting because they are independent to the temperature. I mean, they're related, but the imprints of those signals in temperature and polarization are correlated. So they are generated by the same physics, and they're imprinted in two things. Because the transfer function is so different, so the shape is very different. So if you jointly constrain them, you can vastly increase your constraining power. And also the E modes is even better than temperature because their transfer function has a narrow window in the K. Why it's good? Because those features in power functionality are typically observable. Right? So if you have a larger window function, you kind of like average out the signal and smear them out. But if you have a narrower window function, it's actually more sensitive to the observable feature.
Okay.
Yeah.
Right. You only assume the E mode here in your analysis, but I assume, I think another question
Yeah.
I want to ask is would the B mode play a role, help you probe
Oh.
other aspects?
Yeah, B mode has to do with the gravitational sector. So there could be influences, but not direct. The E mode is guaranteed to be there. It's the same. They have the same source as the T mode from a curvature dimension. So we will measure them, and they will become diagonal for B mode. So they will measure them very well.
Well, but it's a little complicated. So we concentrate on a small patch of sky to look for gravitational waves.
Small patch of
But this
sky.
needs a big patch of sky.
Oh, not as big as big, but small is okay because depending on which modes you are going to. Oh, let me go back to this one. Oh, yeah. Oh, too fast. Sorry. So this is the size I stick. So for example, some of features that we are trying to identify lives here. L equal to 1,000. Okay, so these are statistical noise picked up. Probably, hopefully not, but probably picked up by this feature searching pipelines, and they are fitting these oscillations. So those corresponding to the T modes or E modes at around L equal to 1,000. They are all signals of those. They all belong to the package of predictions of those models. So if you have a small patch of sky, for example, ACT, SPT nowadays, and also CMBS4, they will constrain the polarization mode within this 1,000 a few hundred region. They're actually pretty small sky. Small and large is relative. It's actually pretty small patch of sky in the South Pole. And they will help to constrain the feature here. Okay, now you talk about large sky. That's the purpose of another experiment which we call LIGHTBIRD. LIGHTBIRD is going to be launched in a few years. Oh, nice. Long way. Yeah, LIGHTBIRd. LIGHTBIRd is going to measure the polarization in large scale, right? Include that. Yeah, I didn't include the slides here, but if you look at this slides, the LIGHTBIRd is going to improve a large scale E-mode polarization. So there are actually different experiments play a complementary role in the constraint. And also, what is nice about feature models, when they make predictions, they spread out their predictions between large scale and short scale. They are oscillating in scale. So you predict one predictions at large scale, they will be correlated signal at short scale. So if you have more experiments, that even be better. That's just increasing the constraining power. Yeah.
Do we have more questions to the speaker? If not, then let's give a big applause again.